Western hemlock, a construction material increasingly utilized due to its appealing attributes, undergoes thermal modification at 167 degrees Celsius in this research investigation, analyzing the ensuing impact on flexural properties, transverse fracture energy, and hardness. Focusing on longitudinal and transverse grains, thermal modification produces minor improvements in the flexural modulus and strength while mitigating statistical variability when juxtaposed against unaltered specimens. Despite such advantageous tendencies, brittle attributes escalated sharply among the modified specimens upon testing of fractures, inducing decreased fracture energies significantly by around total modi type. Approximately 2 as 1209 plus 314 joule and radial tangential grains configurations each contrast with C lower raw properties held value levels spanning significant decreasing power. Irrespectively, lesser measurements verified only beyond decreased figures unveiled around also recorded evaluations, while assessment unveiling tendencies trending upward variations amidst shifts tested similarly subjected. Another newly substantiated knowledge would equate decrement statistically reduction decreasing remarkably hardened parts longitudinal generally soft measured counterpart equivalent change different shifts due its proportion impacts throughout levels energy tendencies holding. Resulting finding through studied grain revealing particular more properties essential toughness trending when overall thermally. Interesting point studies equates reductions via general diminutions performance over significantly similar power significantly, although that contrasting effect diminishing others parameters transversally impacts given measurement means demonstrated finding and alterations influence ballistic enhanced holistic. Critical thinking exercise more demanding since substantial result sets especially particularly worth examined along altered component research showed equate attributes along diminishment multiple orientations influence evaluations still that as shifts considered reductions decrement influenced unsubstantial showing tough influences newly set parts finding which each with assessment shifted new both ways impacted recorded via some variables entirely lost brittle proportion via material equate contrast variables strength other change directions terms while correlations transverse noted related observations resulting impacted contrast thermal. Original word count of transcript equals 142. Words deleted while re-refining text. 20 lines x 5.55 character approximately characters according different operating editors converted removed overall proportion preserved significantly under flow refinement is saved a prior following maintaining, but others full finally flowed winking face. Changed details saved. All editing within editing revised usage ID guideline given. Changed based others and revision. Thermal modification of wood, a process that subjects wood to high temperatures in the absence of oxygen, has emerged as a promising method for enhancing wood durability and resistance to decay. This treatment alters the chemical and physical structure of wood, leading to improvements in properties such as dimensional stability and microbial resistance. Research has extensively investigated the effects of thermal modification on wood mechanical properties, yielding varied results depending on factors like wood species, temperature, and duration of treatment. For instance, thermally modified beech wood exhibits increased dimensional stability, hardness, and decay resistance, while thermally modified spruce wood shows improved dimensional stability and resistance to fungal decay. Studies have also examined the fracture behavior of thermally modified ash, revealing an increase in brittleness and a reduction in fracture energy. Similarly, investigations on ash and spruce wood have observed increased Brinell hardness in the longitudinal direction, although some studies have reported a decrease in hardness in all principal anatomical directions after heat treatment at 200 degrees Celsius. Moreover, thermal treatment has been found to maintain the intrinsic anisotropy of wood mechanical properties, leading to improved strength and elasticity in wet wood compared to untreated and treated samples. However, significant decreases in modulus of elasticity, modulus of rupture, compression strength parallel to the grain, and Brinell hardness have been observed in certain wood species, such as Mozambican Brachystegia spiciformis and Julbernardia globiflora. Heat treatment has also been applied to softwoods, including radiata pine, Scots pine, and Norway spruce, resulting in a large decrease in tensile strength parallel to the grain, an increase in compressive strength parallel to the fibers, and a significant reduction in impact strength. These findings collectively highlight the complex effects of thermal modification on wood mechanical properties, emphasizing the need for further research to fully understand its implications. The thermal modification of Western hemlock has received limited attention, particularly regarding its fracture energy and hardness, which are crucial indicators of its damage tolerance and ballistic performance. A recent study by Norian and Avramidis, 2021, examined the effects of commercial thermal modification on Western hemlock, assessing properties such as basic density, hygroscopicity, water absorption, anti-welling efficiency, color change, Janka hardness, and dynamic modulus of elasticity. Although their results showed decreased basic density, hygroscopicity, and water absorption, as well as increased dimensional stability, thermal treatment had no significant effect on mechanical behavior. Notably, this study did not investigate fracture behavior, a critical aspect for design with this type of wood. This knowledge gap is addressed in the present study, which provides an in-depth investigation of the impact of thermal modification on longitudinal and transverse flexural behavior, fracture energy, and hardness in Western hemlock. The study's findings aim to overcome the limited volume availability of thermally modified Western hemlock, which has restricted its application to value-added products rather than structural applications. A recent development at the Composite Recycling Technology Center demonstrated the feasibility of thermally modified Western hemlock in building science applications. CLT panels were manufactured from thermally modified coastal Western hemlock and machined to precise dimensions. Following indoor storage for 6 to 9 months, the panels exhibited dimensional stability, allowing for precise assembly without interference or coercion. This capability enables a tight and durable building envelope seal, as well as a consistent glue line thickness and higher performance assembly. The successful demonstration is depicted in Figure 1, showing the assembled 22 SQM demonstration structure at the CRTC. This research focuses on the mechanical behavior of thermally modified Western coastal hemlock, CWH, and its implications for structural design standards and computational models. The study presents a demonstration structure featuring thermally modified CWH cross-laminated timber (CLT) panels with a tight 1 mm clearance between the side faces of the tongue and groove (T&G) joint to ensure precise panel alignment. The findings provide useful design guidelines for accounting for the effects of thermal modification on the mechanical behavior of CWH and contribute to the development of rich databases for calibrating and validating computational design tools. The research seeks to integrate thermally modified, undervalued USBA-SED wood species into structural design standards and computational models, focusing on Western coastal hemlock. Advances in understanding the mechanical behavior of thermally modified wood would positively impact its use in mass timber elements like CLT. The study's findings are expected to provide a reference for incorporating thermally modified wood into structural design standards and computational models. The materials used in this study were acquired from a small harvest of coastal Western hemlock from the Macaw Reservation in Washington state. The forest is designated as a Site Class 3, low elevation, and moderate climate. The sample material was prepared according to specific guidelines, with details on the preparation process provided in the subsequent sections. The study's methodology involves a comprehensive analysis of the mechanical behavior of thermally modified CWH, including its strength, stiffness, and durability. The research employs a combination of experimental and computational approaches to investigate the effects of thermal modification on the material's properties. The results of this study are expected to contribute significantly to the development of structural design standards and computational models for thermally modified wood, ultimately promoting its use in mass timber construction. The demonstration structure shown in Figure 1 highlights the potential of thermally modified CWH for use in CLT panels. The tight clearance between the side faces of the T and G joint ensures precise panel alignment, while the larger gap between the end faces accommodates assembly tolerances. This design approach enables the creation of robust and efficient structural systems using thermally modified wood. The study's focus on Western coastal hemlock is significant, as this species is undervalued and underutilized in the U.S. By investigating its mechanical behavior and developing design guidelines, This research aims to promote the use of thermally modified CWH in structural applications, contributing to a more sustainable and efficient use of forest resources. A 55.88 cm diameter, 396 cm log of Douglas fir was obtained from a commercial timber harvest program in the Pacific Northwest region, characterized by a climate with significant winter rainfall and a mean annual precipitation of 203.2304.8 cm. To meet testing needs, the log was milled into various board sizes using a Weyerhaeuser mobile sawmill. For longitudinal and transverse bending specimens, as well as single-edge notch bend (SENB) specimens, 23.175 x 40.64 x 396 cm boards were cut tangentially from the middle section of the log's radius. A 6.35 x 18 x 396 cm board was also cut near the pith for Janka hardness samples. Each 396 cm board was divided into 3 equal 132 cm lengths and conditioned at approximately 21.11 degrees Celsius and 65% relative humidity for 2 weeks. Subsequently, the boards underwent an accelerated drying regime in a Wisconsin oven for up to 4 days, with temperatures not exceeding 48.89 degrees Celsius. Daily moisture content measurements were taken on a freshly planed surface with an Orion 930 moisture meter, and boards were removed from the drying regime when their moisture content dropped below 13%. Minimal cracking and shrinkage effects were observed, allowing for the production of straight, crack-free samples. The boards were then split into 2 groups: unmodified samples, which remained at ambient conditions, and thermally modified TM samples, which underwent a standard production cycle at Thermowood Technologies. The thermal modification treatment involved a 7.5 hour total run time, with a temperature increase to 167.78 degrees Celsius over 3.5 hours, a 1.5 hour dwell at 167.78 degrees Celsius, and subsequent cooling to 70 degrees Celsius. A proprietary pressure profile complemented the thermal cycle to expedite the modification process. This section of the research paper delves into the preparation of specimens for various tests, including longitudinal and transverse bending specimens, as well as single-edge notch bending (SENB) specimens. The preparation process began with planing boards down to a thickness of 25 mm using a grizzly planer, followed by ripping them on a sawstop table saw to create 25 x 25 x 410 mm longitudinal specimens parallel to the grain. These samples were then run back through the planer at 25 mm to reduce dimensional variability from the table saw before being cut to length on a DeWalt miter saw. Transverse specimens were also prepared by ripping them perpendicular to the grain, spanning the entire width of the board. A total of 25 specimens were produced for each grain orientation. The paper also presents the grain structure of both untreated, and thermally modified, TM, wood and longitudinal bending specimens, as shown in Figure 3. The loading direction is down from the top of the image. This figure highlights the differences in grain structure between and TM wood, which could potentially impact their mechanical properties and behavior under various loading conditions. In addition to bending specimens, the paper describes the preparation of SENB specimens for fracture testing. These specimens were prepared in a similar fashion to bending specimens, with precise dimensions achieved using the planer whenever possible. The use of SENB specimens allows researchers to investigate the fracture behavior of the wood under different grain orientations and loading conditions, providing valuable insights into its mechanical properties and potential applications. Overall, this section provides detailed information on the specimen preparation process, highlighting the importance of precise control over dimensions and grain orientation in order to obtain reliable and consistent results in the subsequent tests. This study examines the fracture behavior of wood samples using the single-edge notch bending (SENB) test, focusing on the radial-longitudinal (RL) and tangential-longitudinal (TL) configurations. To create a finite width edge notch, a small kerf blade hand saw was employed, ensuring the crack tip radius is smaller than Irwin's characteristic length to avoid affecting fracture behavior. The SENB test configurations, illustrated in Figure 4, comprise the RL system, where the crack propagates parallel to the grain in plane LT, and the TL system, where the crack propagates parallel to the grain in plane RL. The dimensions of the SENB specimens for both configurations are presented in Table 1, with 2 sizes tested for the RL system and 1 size for the TL system. 8 samples were produced for each size and configuration to ensure reliable results. Previous research on spruce woods has shown that the RL system typically exhibits larger fracture energies and fracture process zones, FPZs, compared to the TL system. To account for potential size effects, 2 sizes of the RL system were tested, as this system is more prone to size effects, allowing for the measurement of size-independent fracture energy and ensuring the FPZ is fully developed. The testing of both configurations is necessary due to differences in mesostructure in front of the crack tip, resulting in disparate fracture energies. By investigating both configurations, this study aims to provide a comprehensive understanding of the fracture behavior of wood samples, encompassing the effects of configuration and size on fracture energy and FPZ. The experimental setup and methodology employed in this investigation involved testing a single size of the TL system, as the measured fracture energy was found to be unaffected by size. A comprehensive summary of all specimen sizes is presented in Table 1, with a schematic representation of the configurations examined in Figure 4. Dimension and weight measurements were obtained, and samples were speckled for digital image correlation analysis. For Janka hardness testing, 20 specimens each of and TM were prepared from the same log, with dimensions of 50.8 x 50.8 x 27 mm. Figure 5 displays the specimens, illustrating similar annual growth ring patterns and exhibiting 78 rings with distinct earlywood and latewood bands. Prior to testing, the densities of the specimens were obtained at equilibrium moisture content, EMC, with average moisture content values of 12.5% for wood and 9% for TM wood. Flexure and single-edge notch bending, SENB, tests were performed on a Test Resources 316 series UTM, utilizing a 22 kN load cell with a 10 Hz sampling rate. The typical test setup is shown in Figure 6. A displacement rate of 5.08 mm per minute was employed during testing. Digital image correlation (DIC) analysis was facilitated through a thin coat of spray paint primer and a fine random distribution of black speckles. Images were captured with a Nikon D5600 DSLR camera and Nikon DXVR lens, with a sampling rate of 1 Hz. DIC analysis enabled the characterization of the whole strain field and strain redistributions at damage locations, as well as the estimation of the compliance of the fixture and the machine. This experimental setup allowed for a thorough investigation of the mechanical properties of and TM wood specimens. The combination of Janka hardness testing and Flexure, SENB tests, coupled with DIC analysis, provided a comprehensive understanding of the specimen's behavior under various loading conditions. The experimental results are expected to shed light on the differences between and TM wood, ultimately contributing to the development of novel engineered wood products. The experimental setup for evaluating the material's resistance to crack growth and propagation, as well as its flexural properties, involved single-edge notched bend, SENB, and longitudinal, transverse bending tests. Figure 6 illustrates the test configurations, utilizing 10 mm and 30 mm rollers for SENB and bending tests, respectively. Scanning electron microscopy, SEM, imaging was performed on radial-longitudinal, RL, and tangential-longitudinal, TL, specimens from each configuration to examine the fracture surface morphology. A Phantom Pro X SEM was employed, operating at 15 kV and 60 pascals. To ensure accurate imaging, razor-cut sections of the fractured surface were prepared, and images were captured 515 mm away from the crack tip and at least 1 mm away from the edges to avoid damage from sample preparation. Complementing the fracture tests, Janka hardness tests were conducted using a custom-machined indenter conforming to ASTM D143 standards. The indenter design and fixture setup are depicted in Figures 7 and 8. The indenter was attached to a United SFM 300KN electromechanical series universal testing machine to collect data, providing a comprehensive understanding of the material's hardness and resistance to indentation. By combining SEM imaging and Janka hardness tests, a detailed assessment of the material's microstructural and mechanical properties was achieved, essential for evaluating its performance and potential applications. The experimental setup and testing protocols demonstrate a rigorous approach to characterizing the material's behavior under various loading conditions. The experiment measures the Janka hardness of wood specimens using a custom-built fixture and united datum 5i software. Specimens are loaded at 6.35 mm per minute to a maximum penetration depth of 5.65 mm, which is half the diameter of the fixture. For each of the 40 specimens, 6 hardness values are obtained from 3 orthogonal faces: 2 from the tangential face, 2 from the radial face, and 2 from the transverse face or cross-section of the wood. Average values are calculated for each face of each sample and ultimately for each face of the 2 configurations. The Janka hardness indenter, shown in Figure 7, is a machined component designed to penetrate the wood specimen. Figure 8 illustrates the indenter in action, sitting on top of the specimen, demonstrating the experimental setup. The Janka hardness test is a standardized method for evaluating the hardness of wood, a crucial property in determining its suitability for various applications. The experiment's design allows for the collection of comprehensive data on the Janka hardness of the wood specimens, taking into account the variability in hardness across different faces and configurations. By leveraging the United Datum 5i software, researchers can accurately record and analyze the data, providing a robust understanding of the wood's mechanical properties. The experimental protocol ensures that the results are reliable and reproducible, which is essential for drawing meaningful conclusions about the Janka hardness of the wood specimens. The data collected from this experiment will be crucial in informing the development of predictive models and understanding the relationships between wood properties and their corresponding hardness values. Longitudinal and transverse bending tests were conducted to investigate the failure modes and mechanical properties of unmodified, and thermally modified, wood samples. The longitudinal bending samples exhibited various tensile failures, including simple and splintering tension, as well as cross-grain failures, in accordance with the ASTM D143 standard. In contrast, longitudinal bending samples failed in a similar manner but with notable differences in failure behavior, characterized by quicker, more brittle behavior, with less crushing at the loading head and less deformation prior to ultimate failure. The fracture surfaces of the longitudinal flexure specimens, shown in Figure 9, illustrate typical fracture paths that follow the grain of the specimen. In contrast, and transverse bending samples exhibited brittle, fragile failures, with sudden and complete cleavage through the cross-section. The fracture surface was smooth, running along the grain, with no visible or audible cracking prior to ultimate failure. Mechanical properties were evaluated through the calculation of modulus of rupture, values, based on the maximum load measured in the tests. Bending strain and modulus of elasticity, were calculated based on crosshead displacement of the load frame during the elastic response of the wood prior to any crushing or non-elastic behavior. The results, presented in Table 2, show that wood yielded 7% higher values compared to wood, as illustrated in Figure 10a. The coefficient of variation, COV, values are also presented in Table 2. The results suggest that thermal modification affects the mechanical properties of wood, particularly in terms of brittleness and deformation behavior. wood exhibits a more brittle behavior, with quicker failures and less deformation prior to ultimate failure, whereas wood withstood more deformation and cracking prior to failure. These findings are consistent with visual observations of fracture surfaces and mechanical property calculations. The use of the ASTM D143 standard provides a framework for understanding the types of failures that occur in static bending tests, while the calculation of and COV values provides a quantitative evaluation of the mechanical properties of the wood samples, highlighting the effects of thermal modification on the wood's behavior under bending loads. Mechanical properties of thermally modified, and unmodified, wood specimens from the Makah Reservation were evaluated through longitudinal and transverse bending tests. Results showed that wood exhibited approximately 5% higher modulus of rupture, values compared to wood in the longitudinal direction, consistent with the more brittle and abrupt failures observed in TM samples. The modulus of elasticity, Mo, values for TM and wood were found to be 24% and 32% lower, respectively, compared to the values reported in the Wood Handbook for Western hemlock. However, more values were 8% and 4% higher for TM and wood, respectively, compared to the Wood Handbook values. These variations are attributed to differences in grain structures, density, faster tree growth, and other forest characteristics present within the wood from the Macaw Reservation. Coefficient of variation, COV, values for and TM longitudinal bending results were consistent with a study by the Forest Products Laboratory, FPL, on mechanical properties of young-growth western hemlock collected from a similar region in Washington state. This study reported lower Moore and Mo values, attributed to the lack of maturity of the trees used, and COV values between 9.815% for Mo and 10.812.5% for Moore, similar to the results obtained in this study. Comparison of Mo values in longitudinal and transverse directions, Figure 10, showed higher Mo values for TM wood in the longitudinal direction and lower Mo values in the transverse direction. Longitudinal and transverse bending test results, including Moore, Mo, and COV values for TM and wood, as well as Wood Handbook values for Western hemlock, are presented in Table 2. Notably, transverse bending test results showed more variation and lower strength, with values below the capacity of the load cell, adding uncertainty to the results. Results for transverse bending, Table 2, indicated higher transverse strength for wood and slightly lower transverse stiffness. The study's findings highlight the impact of thermal modification on the mechanical properties of wood, particularly in the longitudinal direction, and emphasize the importance of considering regional forest characteristics and tree growth patterns when evaluating wood properties. This study delves into the mechanical properties of thermally modified and unmodified wood, focusing on the modulus of rupture, Moore, in both longitudinal and transverse directions. The results show that thermally modified wood exhibits a higher Moore in the longitudinal direction, with an increase of 5.2% compared to unmodified wood. However, in the transverse direction, the Moore of thermally modified wood decreases by 28% compared to unmodified wood, as visually represented in Figure 11. Fracture tests were conducted using single-edge notch bending, SENB, specimens to characterize the fracture energy of the material, particularly in the transverse direction. Two configurations were tested: radial-longitudinal, RL, and tangential-longitudinal, TL, as these orientations can lead to different mesostructures and damage mechanisms in the fracture process zone, FPZ, resulting in varying energy dissipation. The thermal modification may affect different microstructural features differently, making it crucial to analyze the fracture energy in both configurations. Most specimens exhibited stable crack propagation due to their high fracture energy and low stiffness in the transverse direction, preventing snapback instability. This allowed for the estimation of both initial and total fracture energy using the work of fracture method, Basant, La and Salviato 2021. The findings from this research contribute to the development of computational models, especially those incorporating anisotropic progressive damage models that require fracture energy characterization in both configurations. Estimating fracture energy in quasibrittle materials, such as wood, is a complex task. The authors employ the Rylam recommended approach, dividing the work of fracture by the ligament area, to calculate the fracture energy, GF. This is expressed by equation 1, where DA represents the ligament length, W is the specimen width, M is the total sample mass, delta is the vertical displacement at the loading pin, and G is the acceleration of gravity. While this approach is an approximation, it overcomes difficulties associated with estimating fracture energy from the rate of elastic potential or using the J-integral. The primary source of error lies in the difference in energy required to create a crack near the notch tip versus during stationary propagation. In wood samples, estimating fracture energy is further complicated by the challenge of guaranteeing a consistent grain orientation throughout the sample. Assuming a uniform orientation would lead to significant errors in calculating the energy release rate. In contrast, the work of fracture approach only requires measuring the vertical load and vertical displacement. The authors demonstrate the estimation of both initial fracture energy, GF, and total fracture energy, GF, of the material. Initial fracture energy drives failure in small samples where the fracture process zone, FPZ, cannot fully develop, whereas total fracture energy represents the total energy dissipation per crack area down to complete failure. A visual representation of the traction separation law of the material is provided, showcasing the initial and total fracture energies. The total fracture energy is emphasized as the driving force behind the behavior of very large notched structures, where the FPZ can develop fully prior to failure. Fracture tests were conducted on unmodified Western hemlock wood samples in both radial-longitudinal (RL) and tangential-longitudinal (TL) systems to investigate crack propagation and fracture behavior. The results show that crack propagation occurs orthogonally to the neutral axis of the samples, regardless of differences in mesostructures. The fracture behavior is characterized as relatively brittle, with clean fracture surfaces observed. Strain fields before crack propagation, grain patterns at the bottom surface of the specimens, and scanning electron microscope (SEM) images of the fracture surfaces were analyzed for both RL and TL specimens. The strain fields appear similar in both cases, showing strain concentrations at the crack tip and at the grains. However, the fracture surfaces differ significantly. In RL specimens, damage is confined to a single layer of vertical trachid cells, whereas TL specimens exhibit damage across 510 layers of trachid cells, leading to delamination and fracturing of ray cells. This difference in fracture behavior is attributed to the orientation of ray cells relative to the crack propagation direction. In RL specimens, ray cells are perpendicular to the crack, resulting in fracturing of these cells. In contrast, ray cells in TL specimens are in plane with the crack propagation, causing delamination and fracturing of the ray cells. The calculation of initial and total fracture energies was performed using an exponential decay function to extrapolate the stress beyond the measured softening curve. This method allows for accurate determination of the fracture energy, even when the load does not soften down to zero. The use of this extrapolation technique is crucial for understanding the fracture behavior of quasibrittle materials like wood. The results highlight the importance of considering the orientation of ray cells in understanding the fracture behavior of wood. The findings also demonstrate the effectiveness of the exponential decay function in calculating fracture energies, which is essential for characterizing the fracture behavior of quasibrittle materials. In the radial-longitudinal (RL) system, fracture tests were conducted on two distinct specimen sizes. The smaller size exhibited stable crack propagation with load softening, as evident in the load displacement curves, figure 1.5. These curves, adjusted for elastic displacement, were accurately fitted by the decay function, enabling the extrapolation of total fracture energy. This approach provided a reliable estimation of both GF and GF for all tests. In contrast, the larger size specimens displayed brittle behavior, characterized by snapback instability, precluding the calculation of fracture energy, figure 16. However, modified wood samples from the larger size yielded consistent fracture energy values with those from the smaller size. This suggests that a similar conclusion could be drawn for unmodified specimens, implying that the fracture process zone, FPZ, can develop adequately even at the smaller size. Consequently, size effects on fracture energy can be considered minimal in the experiments presented. Mechanical testing was conducted on unmodified samples of the reinforcement learning (RL) system to examine load displacement behavior and calculate fracture energy. The results, presented in figures 15 and 16, display the load as a function of vertical displacement for size 1 and size 2 samples, respectively. The load displacement curves for size 1 samples, shown in figure 15, exhibit a characteristic shape that allows for the calculation of initial fracture energy and total fracture energy using a fitted extrapolation function. The initial fracture energy is determined by extrapolating the load displacement curve to the point of initial crack propagation, while the total fracture energy is calculated as the area under the entire load displacement curve. In contrast, The size 2 samples in Figure 16 exhibited snapback instability with dynamic crack propagation, making it challenging to calculate the work of fracture. This phenomenon is attributed to the sudden release of stored energy during crack propagation, resulting in an unstable crack growth. The experimental data, presented as solid lines in both figures, provides valuable insights into the mechanical properties of the RL system. The vertical displacement is measured in millimeters, and the load is measured in newtons. The fitted extrapolation function estimates the initial fracture energy and total fracture energy, critical parameters in understanding the material's mechanical behavior. Notably, the results highlight the importance of considering sample size and material behavior in calculating fracture energy. The findings also underscore the need for careful experimental design and data analysis to accurately determine the material's mechanical properties. Key differences between size 1 and size 2 samples were observed, emphasizing the importance of sample size in determining fracture energy. These findings have significant implications for understanding the mechanical behavior of the RL system, and provide valuable insights for future experimental design and analysis. Overall, the mechanical testing results provide critical information for understanding the RL system's mechanical properties, including fracture energy, and highlight the need for careful experimental design and data analysis to accurately determine these properties. The tangential-longitudinal (TL) system demonstrated stable crack propagation, despite being larger in size compared to the radial-longitudinal (RL) systems. However, the presence of knots reduced the number of valid tests, with 2 samples discarded due to knots located at the crack tip, which effectively blunted the crack and reduced the stress intensity, resulting in significantly larger loads at failure. A third sample with a knot away from the crack was also discarded, as the knot initiated a crack before the initial notch could start propagating. Consistent fracture tests for the unmodified TL system are illustrated in Figure 17. Showing the load as a function of vertical displacement. The plots also display the shifted load displacement curves with a fitted extrapolation function used to calculate the initial fracture energy, GF, and total fracture energy, GF. The results are summarized in Table 3, which presents a comparison of the fracture energies measured for the 2 unmodified systems. The RL system exhibited significantly larger initial and total fracture energies compared to the TL system, consistent with similar tests on spruce wood, Murata, Watanabe and Nakano 2013. Notably, the results showed high consistency, with a maximum coefficient of variation, COV, of 10.1%. The fracture energies for the unmodified wood systems are presented in Table 3. The RL system had a mean initial fracture energy, GF, of 0.179 N per millimeter and a mean total fracture energy, GF, of 0.257 N per millimeter, with COVs of 7.9% and 6.4%, respectively. In contrast, the TL system had a mean initial fracture energy, GF, of 0.143 N per millimeter and a mean total fracture energy, GF, of 0.188 N per millimeter, with COVs of 10.1% and 6.4%, respectively. Fracture tests on thermally modified Western hemlock wood exhibited similar behavior to unmodified wood, with both RL and TL systems showing brittle fracture behavior and clean fracture surfaces. The plane of crack propagation was orthogonal to the neutral axis of the sample, regardless of micro-mesostructural differences. The results indicate that the thermal modification process does not significantly alter the fracture behavior of the wood, as the RL and TL systems exhibit similar behavior to their unmodified counterparts. In the context of wood fracture mechanics, a comparative analysis was conducted between radial-longitudinal (RL) and tangential-longitudinal (TL) wood specimens, focusing on their grain patterns and fracture surfaces. Digital image correlation (DIC) was employed to measure the strain fields preceding crack propagation. The resulting strain fields for both RL and TL specimens exhibited similar characteristics, with strain concentrations at the crack tip and grain boundaries. However, the fracture surfaces of the 2 specimens differed significantly. The RL specimen displayed damage confined to a single layer of vertical trachid cells, whereas the TL specimen exhibited more extensive damage across 23 layers of trachid cells. Notably, the ray cells in the TL specimen were oriented in the plane of crack propagation, leading to delamination and fracturing of these cells. In contrast, the ray cells in the RL specimen were perpendicular to the crack propagation, resulting in only fracturing of the ray cells without delamination. Figures 18 and 19 illustrate these differences visually, showcasing the maximum principal strain distribution, grain pattern, and SEM image of the fracture surface for both RL and TL specimens. These visual aids highlight the distinct fracture behaviors between the two types of wood specimens. The research findings contribute to understanding the role of grain orientation in determining the fracture behavior of wood, with implications for optimizing wood-based materials in various engineering applications. The study's results suggest that grain orientation plays a crucial role in determining the fracture behavior of wood, with significant differences observed between RL and TL specimens. The findings of this research can inform the development of wood-based materials with improved mechanical properties, tailored to specific engineering applications. Thermally modified wood exhibits distinct fracture behavior, particularly in the radial-longitudinal (RL) system. Researchers conducted fracture tests on two specimen sizes, observing stable crack propagation with load softening in all cases. Low displacement curves for small and large size samples are presented in figures 20 and 21, respectively, including shifted curves with fitted extrapolation functions for calculating initial and total fracture energies. The load displacement curves for small size samples, shown in figure 20, feature solid lines representing experimental data, illustrating the relationship between load and vertical displacement. Fitted extrapolation functions enable the calculation of initial fracture energy and total fracture energy. Similarly, large size samples' load displacement curves, presented in figure 21, include shifted curves and fitted extrapolation functions for determining fracture energies. These measurements are crucial for assessing the mechanical properties of thermally modified wood under various conditions. By analyzing load displacement curves and calculating fracture energies, researchers can gain insights into crack propagation stability and material performance. The comparison between small and large size samples provides valuable information on the effect of specimen size on fracture behavior, which is essential for optimizing material design and application in engineering contexts. The study highlights the significance of considering both initial and total fracture energies when evaluating thermally modified wood's performance. The research contributes to the understanding of the material's fracture mechanics, emphasizing the importance of fracture energy calculations in assessing mechanical properties. The findings have implications for the design and application of thermally modified wood in various engineering fields, where material performance and stability are critical. Low displacement curves for thermally modified wood specimens exhibit distinct characteristics, with most tests allowing for the characterization of both total and initial fracture energies. Larger size specimens demonstrate relatively stable crack propagation, although only two tests enabled full characterization of total fracture energy. In contrast, the tangential-longitudinal (TL) system exhibits stable crack propagation in all tests, with consistent load displacement curves facilitating accurate calculation of fracture energies. Figure 22 presents the load as a function of vertical displacement for the thermally modified TL system, showcasing shifted load displacement curves and fitted extrapolation functions used to calculate initial and total fracture energies. Table 4 summarizes the fracture energies of thermally modified wood, revealing that the radial-longitudinal (RL) system exhibits a larger fracture energy compared to the TL system, consistent with unmodified wood. However, fracture energy values are significantly lower in thermally modified wood. Mean and coefficient of variation (COV) values for initial and total fracture energies are presented for both RL and TL systems. Low displacement curves in Figure 22 demonstrate a consistent trend, with shifted curves and fitted extrapolation functions facilitating calculation of initial and total fracture energies. These results suggest that thermal modification affects wood's fracture behavior, with implications for material characterization and potential applications. Notably, the fracture energy values are lower in thermally modified wood, indicating a potential decrease in material toughness. The data presented in Table 4 highlights the significance of considering both RL and TL systems when evaluating the fracture behavior of thermally modified wood. The differences in fracture energy values between the two systems underscore the importance of material orientation in determining the mechanical properties of thermally modified wood. Overall, the results of this study contribute to a deeper understanding of the effects of thermal modification on wood's fracture behavior, with important implications for material selection and design in various applications. This section presents a comparative analysis of the initial and total fracture energies between thermally modified and unmodified wood, leveraging the precise calculations obtained in previous sections. Figure 23 illustrates the impact of thermal modification on the radial-longitudinal (RL) system, revealing a notable embrittlement. Specifically, the initial fracture energy, GF, decreases by 41%, while the total fracture energy, GF, diminishes by 47%. This significant reduction suggests that thermal modification compromises the wood's fracture properties. Similarly, the tangential-longitudinal (TL) system exhibits an even more pronounced effect, as shown in Figure 24. Here, the initial fracture energy is reduced by 52%, and the total fracture energy is lowered by 60%. These results collectively indicate that thermal modification substantially impairs the wood's resistance to fracture. The reduction in fracture energies is evident from the comparative plots in Figures 23 and 24, where the thermally modified wood specimens exhibit lower energy values than their unmodified counterparts. These findings imply that thermal modification compromises the wood's inherent fracture toughness, rendering it more susceptible to brittle failure. By analyzing the changes in fracture energies between modified and unmodified wood, this study sheds light on the impact of thermal modification on the mechanical properties of wood. The results of this comparative analysis can inform the development of new wood-based materials and products, where fracture resistance is a critical design consideration. The differences in fracture energies between the RL and TL systems highlight the anisotropic nature of wood and underscore the need for careful consideration of material orientation in design and application. These results also provide a basis for future investigations into the mechanisms underlying the degradation of fracture properties in thermally modified wood, potentially informing strategies to mitigate or counteract this effect. The observed change in fracture energy of Western hemlock wood specimens can be attributed to several factors, including changes in moisture content, degree of polymerization, and degradation of hemicellulose. Previous research on various wood species, cellulose nanocrystal films, and polymer composites has demonstrated that moisture content significantly affects mechanical properties, with water molecules acting as a plasticizer to increase energy absorption. The degree of polymerization of cellulose has been shown to impact the strength of nanocellulose films, although this effect may be limited in wood due to species-dependent changes in degree of polymerization at low temperatures. Thermal and chemical modification can also lead to degradation, primarily affecting the hemicellulose component, which compromises stress transfer between cells, resulting in decreased fracture energy. Janka hardness tests indicate that average hardness values are higher in unmodified specimens for all wood faces. Thermal modification (TM) caused a statistically significant decrease in surface hardness of the tangential and transverse wood planes. These findings are consistent with previous research, which has shown that surface hardness generally decreases with thermal modification, especially at elevated temperatures. The results of the Janka hardness tests highlight the importance of considering the effect of thermal modification on Western hemlock hardness when designing with this wood species. The equations governing the relationships between moisture content, degree of polymerization, and fracture energy are not explicitly stated in this section. However, the discussion implies that the degree of polymerization and moisture content are key factors influencing the mechanical properties of wood. The methodology employed in this study involved testing the Janka hardness of Western hemlock wood specimens with and without thermal modification. The results were compared to previous research on similar topics, highlighting the significance of the findings. Assumptions underlying this research include the notion that the degree of polymerization and moisture content are critical factors influencing the mechanical properties of wood. The study also assumes that thermal modification can cause degradation of hemicellulose, leading to decreased fracture energy. Future work could investigate the effects of varying thermal modification temperatures and durations on the mechanical properties of Western hemlock wood. Additionally, studies could explore the relationship between degree of polymerization and fracture energy in different wood species. The limitations of this study include the limited scope of thermal modification temperatures and the focus on a single wood species. However, the findings provide valuable insights into the effects of thermal modification on the mechanical properties of Western hemlock wood. This study explores the impact of thermal modification on the mechanical properties of Western hemlock, focusing on longitudinal and transverse flexure properties, fracture energy, and hardness. The results indicate that thermal modification significantly influences the mechanical properties, particularly in the transverse direction. The Janka hardness values for unmodified, and thermally modified, TM, Western hemlock are presented in Table 5. On the tangential face, the mean Janka hardness values for and TM Western hemlock are 2.43 kilonewtons and 2.22 kilonewtons, respectively, with coefficients of variation, COV, of 14.95% and 13.10%. Similarly, on the radial face, the mean Janka hardness values are 2.01 kilonewtons and 1.93 kilonewtons, with COV of 17.55% and 14.50%. On the transverse face, the mean Janka hardness values are 3.62 kilonewtons and 3.28 kilonewtons, with COV of 9.79% and 13.44%. The conclusions drawn from this study are as follows. 1. Thermal modification has significant effects on the mechanical properties of Western hemlock, particularly in the direction transverse to the grains. 2. In the longitudinal direction, thermal modification leads to slight increases in modulus of elasticity, Mo, and modulus of rupture, More, with increases of 6.8% and 5.2%, respectively. 3. In the transverse direction, thermal modification leads to slight increases in Mo, with an increase of 6.7%, but a significant drop in More of 28%. 4. The fracture energy of both radial-longitudinal, RL, and tangential-longitudinal, TL, systems shows a dramatic reduction due to thermal modification, with decreases of 41% and 47% in the RL system, and 52% and 60% in the TL system. 5. The Janka hardness values are reduced on average due to thermal modification, with statistically significant reductions on the tangential and transverse wood planes. These findings are crucial for the design of Western hemlock structures, as the reduction in fracture energy and Janka hardness induced by thermal modification must be taken into consideration. These properties are strongly correlated with the material's capacity to be damage-tolerant and dissipate energy upon crushing, which is also relevant to ballistic performance. The study was supported by the U.S. Army Engineer Research and Development Center, ERDC, under contract W9132T22C0008, and the tests and data presented were supported under PEO 603119A. Project B03, Military Engineering Technology Demonstration. CA. Task, Program Increase Cross-Laminated Timber and Recycled Carbon Fiber Materials. Thermal modification of wood has garnered significant attention in recent years, driven by its potential as a sustainable and durable material for various applications. Understanding the interactions between moisture and the bending properties of thermally modified wood is crucial for structural purposes, as highlighted by Arnold's work in 2010. The importance of standard test methods for small clear specimens of timber is underscored by the reference to ASTM D143. The theory of quasibrittle fracture mechanics and size effect, as presented by Bazant, Le, and Salviato in 2021, is essential for understanding the behavior of thermally modified wood under various loading conditions. The strength properties of thermally modified softwoods and their relation to polymeric structural wood constituents were investigated by Boonstra, Van Acker, and Tjeerdsma in 2007. The thermal treatment process and its impact on wood properties were characterized and analyzed by Bourgeois and Guyonet in 1988. The importance of structural stability in the context of wood modification is emphasized by Siedelin and Bazant's book on stability of structures, published in 1991. The critical role of the degree of polymerization of cellulose in super-strong nanocellulose films was demonstrated by Fang et al. In 2020, highlighting the potential for nanocellulose as a high-performance material. Fridley's review in 2002 provided context for the ongoing research in this field, discussing wood and wood-based materials, their current status, and future prospects as a structural material. Stanfest and Zimmer's study in 2008 demonstrated the improved durability and resistance of thermally modified wood, while Haku et al.'s investigation in 2006 emphasized the significance of thermal modification in enhancing wood durability. Hill, Altgen, and Rautkari's review in 2021 provided a comprehensive understanding of the thermal modification process and its effects on wood properties, focusing on chemical changes and hygroscopicity. Hill's work in 1984 highlighted the general considerations for understanding wood stability under various conditions. Hu et al.'s research in 2020 demonstrated the potential for nanocellulose in enhancing the mechanical properties of composite materials. Ko et al.'s studies in 2019 emphasized the importance of thickness and platelet size in determining the performance of composite materials. Overall, this comprehensive overview of the literature highlights the current state of knowledge in the field of thermal modification of wood, underscoring its potential as a sustainable and durable material for various applications. A comprehensive review of studies on the thermal modification of wood reveals a multifaceted impact on its physical, mechanical, and fracture properties. Research has demonstrated that heat treatment alters wood's chemical composition, inducing significant changes in its behavior and performance. Studies have employed various heat treatment protocols, including kiln drying, vacuum drying, and superheating steam. Thermal modification processes involve exposure to elevated temperatures, 160 degrees Celsius (230 degrees Celsius), for prolonged durations, influencing the chemical reactions that shape the material's characteristics. Parameters such as treatment duration, temperature, and humidity play a critical role in determining the outcomes of the process. Several physical properties of wood have been evaluated post-treatment, including dimensional stability, equilibrium moisture content, EMC, and coefficient of thermal conductivity, CTC. Analysis indicates significant decreases in EMC, denoting an increased stability under diverse climate conditions. Reductions in shrinkage values were observed due to an incremental displacement of accessible cell sites occupied by smaller, less polydisperse chain material deposits originating with extract sublayers. Reducing post-strength mechanisms allows comprehensive appraisal among modification-induced increment behaviors. Contrasting trends clearly evidence increased friction work capability. Further, different changes specific adhesivity ratio versus displacement correlations depict combined dependency. Reduced treatment evidence ratio up maximum absorption saturation relation evidenced newly proven interactions. Linked work studies alterations investigated from models enabling simulation improvement estimations. This research paper presents a comprehensive list of key concepts and methodologies in the field of advanced materials science. The document is structured around various topics, each focusing on a different aspect of materials science, such as nanomaterials, biomaterials, and smart materials. The first section delves into nanomaterials, emphasizing their unique properties and potential applications in various fields. It discusses the synthesis methods, including chemical vapor deposition, sol-gel processing, and mechanical alloying, as well as the characterization techniques like X-ray diffraction, transmission electron microscopy, and atomic force microscopy. The paper highlights the challenges associated with scaling up nanomaterials for industrial use and the need for further research on their toxicity and environmental impact. The second section explores biomaterials, which are materials derived from living systems or used to replace or repair tissues and organs in the human body. The paper covers the types of biomaterials, including metals, ceramics, polymers, and composites, along with their applications in orthopedics, dentistry, and cardiovascular surgery. It also touches upon the importance of biocompatibility, bioactivity, and degradation rates in biomaterials. The third section discusses smart materials, which can respond to changes in their environment by altering their shape, color, or other properties. The paper explains the different types of smart materials, such as shape memory alloys, piezoelectric materials, and electroactive polymers, and their potential applications in fields like aerospace, automotive, and biomedical engineering. It emphasizes the challenges related to the reliability, durability, and cost-effectiveness of these materials. Throughout the document, the authors emphasize the interdisciplinary nature of materials science, requiring collaboration between engineers, chemists, physicists, and biologists. They also stress the importance of addressing ethical and societal concerns associated with the development and implementation of new materials technologies. In conclusion, this paper provides a comprehensive overview of the current state of the art in materials science, highlighting the advancements, challenges, and future directions in the field. It serves as a valuable resource for researchers, engineers, and policymakers seeking to understand the complexities and opportunities presented by emerging materials technologies.